Uh, Good morning, everyone. I'm very sorry. My apparently urgent law. So I'll be speaking in English. I'll be talking a little bit about what we call envirotyping, which is sort of a new approach in agriculture. It includes a lot of monitoring, but also what we do after the monitoring. So let's start with some background. So we know this month we have reached 8 billion people on Earth, right? And the projection is that in the next 25 years, we'll reach around 10 billion, and then the rate of growth of population will slow down, right? But as the population grows, we need to also feed them. And the United Nations estimates that we'll need to increase our yield by 70% from our present yield numbers by 2050. How do we do that? Because this is not a small number, right? So if we look at the sources of agricultural output growth, so these are in terms of percent over the previous decade, right? So this is from the 60s until about now. So there's not much relative growth, but there's still some growth, right? So this is the rate of growth, and what are the contributing factors? Some of it comes from increasing the area of agricultural land. So we do agriculture in more larger areas, although that is now coming down again. We don't have much agricultural land available. The other is increasing irrigation to the area that we already have under agriculture. Again, that is coming down. The cost of irrigation is going higher. Water is not available everywhere easily. So irrigation is not an option to increase the yield. One of the largest was the density of inputs per area. So we plant more seeds, we apply more fertilizer, we apply more pesticides so that we protect the crops and we get more yield. Right? But then there is only so much that the chemistry can do. And lately we've discovered that a lot of the chemicals can have other health effects on humans, so we don't want to use them. Although they may increase the yield, they are also harmful. Right? So that percentage has also come down. And the factor that is contributing the most recently is what we call improvements in total factor productivity. So what is that? So you have better seeds, they are genetically improved, they are bred for certain locations. You have better management practices. You know exactly when to provide water, how much to provide, things like that. And also better fertilizers. So these are the factors that are contributing the most now, and we need to improve this section. So if you look at modern agriculture, there have been three major revolutions. The initial one was in the early 1900s with mechanization. We got the tractors, we got the tillers. We did not need that many people to work on the farms anymore. It was faster, more efficient. And one farmer at that time could feed 26 people. Then in the mid 1900s came the Green Revolution, biotechnology. Right? And with that, the number of people fed by the farmer increased a lot. Now around more than 150 people were fed by that same farmer. And now we are in the third wave. It is called the digital revolution, where we are creating awareness or generating knowledge about our farms using digital technologies, data analytics, things like that. And now a farmer can feed more than 250 people, right? But we still need to improve, right? This is not going to be sufficient to feed all the people by 2050. So let's see some facts again, going back to the background. Agriculture employs worldwide more than 1 billion people. And so it is a good source of income for a lot of people. There's a 2.4 trillion US dollar industry. But 1/3 of the food that is produced on average is wasted. Between the farm and the seller, between the seller and the user, after the user buys it, just think how much food do we waste every day, right? It sits in the fridge for 2 weeks and then we throw it out. You go to a restaurant, they prepare more food. So about 1/3 of the food is wasted. Agriculture is one of the largest contributors of greenhouse gases. Right? It's also one of the most benefited by greenhouse gases. So that might be one of the reasons. And it is also the #1 user of fresh water. By this, it is also the #1 polluter of fresh water. Okay. Agriculture has been traditionally information poor, but lately it is getting more and more data rich. Okay. How is it becoming data rich? As I said, when even 10, 15 years ago, there was not much information or data about agricultural practices. But now, this is a table from a World Bank report from 2018, and this is just the digital tools being used for agriculture in Russia. This is not global, just in Russia, right? And a few years before this report came out, there were not this many companies working on the digital aspect of agriculture. But you see that a lot of companies work on capturing information from the farms, right? So you have sensors in the ground, you have sensors on drones, you have remote sensing from satellites, you have real-time data, you have data from historic records that have been noted down by agronomists for maybe 20, 30, 40 years. And then you also have these scientific models that give you projections about the crop growth. Okay. So some of those sensors could be like on the field, you have robots going into the fields, taking measurements of the soil health, of the plant health, or it could be by drones. Lately, globally, there has been a push towards what is called critical zone observatories. So, critical zone is the zone between the air and the bedrock. So, we are not touching the petroleum part, but everything between the air and the rock, right? Because that is the zone that is critical for plant growth. And you see that there are now a lot of observatories which collect a lot of synchronized data about different aspects of agriculture or even just the environment. Unfortunately, see, there is zero in Russia. Right? So we are trying to change that now, but right now the status is 0. So what are some of the ways that the critical zone observatories collect this information? It could be on-ground sensors. This is called a neutron probe or a cosmic ray neutron sensor. What it does is it measures how wet the soil is based on the neutrons that are reflected back from the soil. So this tube has a sensor which collects the number of neutrons that are reflected back. So the direct neutrons from the atmosphere are at a different speed compared to what is reflected back. Right? You have truck-mounted sensors. Unfortunately, I think it's got cut over there, where you can see the how the soil is, how the ground is below. You have sensors that monitor the fluxes or the evaporation, transpiration from the plants, from the soil. Similarly, this is another instrument called the scintillometer, which again measures the radiation and the fluxes. And of course, the regular weather stations that we all get information from on our phones, right? You can also have sensors mounted on planes to monitor the health of these crops, or it could be helicopters, drones, large or small, or it could be by satellites. There are a number of satellites right now which are monitoring the soil moisture, the soil salinity, the ocean salinity, things like that. So this is a satellite by NASA called SMAP, Soil Moisture Active Capacitor. You have Sentinel, different kinds of satellites, and lately the push has been towards microsatellites, right? So mini, small satellites about a shoebox size. So instead of spending $1 billion on one satellite that may go up and something goes wrong and you get no data, which is what happened with SMAP. Instead of that, you send up 50 smaller ones, which cost maybe $1 million each. Right? So even if a few of them go bad, you still have data from the others. And so mainly, we see that a lot of the data is resolution dependent. So what do we mean by resolution? We have three kinds of resolution, especially for remote sensing: spatial, temporal, and spectral. So what is spatial resolution? It is simply the measure of the smallest object that can be clearly seen from those pictures. Right? It is the linear dimension on the ground that is represented by each pixel of the image. So for example, this is an image at 250 meters resolution. So each pixel is 250 meters by 250 meters. Can anybody tell me what this shows? No, right? So this is the same thing at 30-meter resolution. Now you see that there are some differences, more heterogeneity. It is not so homogeneous. At 10 meters, maybe a river or a road, something like that, right? And this is at 1 meter. You can clearly see the trees, you can see the buildings, you can see the roads, right? So this is spatial resolution. Temporal resolution is simply how often the satellite comes back to the same point again. So it might be every day, it might be once in a week or 2 weeks, it might be once in a month. It depends on the sensor design and the orbit design. Right? So the sensor design is basically the spatial resolution of the sensor, as well as how much on the ground it covers in one shot, one snapshot. The orbit design, of course, is the orbital path, whether it is going over the poles, over the equator, in which direction, and at what speed. Spectral resolution is something which is very critical for agriculture use. It is the number and width of the bands, spectral bands in the sensor. Right? So if you take the visible part of the electromagnetic spectrum, this is from violet to red, right? And then you have ultraviolet on this side and infrared on the other. So as an example, if I had a sensor with a spectral resolution of 4 bands, this is what it would measure. this is how it would give. But if I had a sensor with 10 bands of resolution, you would get much better information, right? Of course, higher the number of bands or the higher the spectral resolution, the more expensive the sensor. Currently, a lot of the satellites are in the multispectral category, which have about 8 bands. There are 3 that I know of satellites which have hyperspectral sensors on them, which is hundreds of bands. And now we are already talking about ultraspectral, which would have thousands of bands. So we'll see later why the bands are important. So not all applications require high spectral resolution, high temporal resolution, high spatial resolution, right? If you're looking at climate modeling, climate does not change in a day or a week or a month or even a year, right? It takes a long process. It's over maybe a century, 10 years, decades. So the temporal resolution can be pretty high. And also, you don't talk about it in terms of a farm field. Talk about it in terms of a region or continent. But if you're doing emergency response or even precision agriculture, you need that resolution to be very high. So what are some of the things that we can monitor? So this is the Gulf, Middle East, Saudi Peninsula. This is Saudi Arabia. If you look at this place in the northern part, in 1987, this was how it was. Okay. It does snow here for a few days every year. It gets cold, and then within a week or so, the snow melts, and that is why you see these small dry riverbeds where the snow melt flows. Right? But otherwise, this is all desert. This was in 1991. So 87, 91, 4 years later. All these dots that you see are farms. So how are they growing things in the desert? This is by drilling down about a kilometer into the earth to access aquifers which are millions of years old. And each of these dots is about 1 kilometer in diameter. Okay. So they're using fossil water at a rate that they cannot replace. 2000, and by 2012 there are about 1,000 of these farms. So just imagine how much water is being used by each one of these dots. There is a lot of evaporation, transpiration because of the high heat and dry nature of this desert. So they're just using up much more water than would be used up in a tropical area or even here. So there's a lot of studies going on about how much the water use is and how long the aquifers could last. So just 25 years to go from here to here. This is a snapshot of rapeseed flowers in the Kursk Oblast. This whole region is planted with rapeseed, but only these have flowers. So what does that tell us? These guys planted earlier compared to the others, right? Also, for some other uses, we can monitor if, in fact, it is rapeseed that is being planted, or is it something else, or is it just grass that is growing, but the farmer tells the government that he is growing crops, right? You can monitor air pollution. Why is air pollution important for agriculture? The point is, agriculture depends on, the plants depend on sunlight. for photosynthesis, right? If there is a lot of pollution, your weather still says that it is clear, but the pollution reduces the amount of sunlight the plant gets, and its productivity decreases, right? So it's not just the clouds that we need to monitor, we also need to see about high pollution. You can monitor weather conditions. For example, at one time in 2019, there were 4 named storms in the Western Hemisphere, and there were a couple more that were getting ready to grow up, right? So if I was living somewhere here, I would know that for the next few weeks, it is going to be one storm after the other. So I'm not going to water my plants. I'm going to run away from there, right? Similarly, the floods during monsoons. You can also monitor forest fires, like the Siberian forest fires a couple of years ago. You can even model them. So you can model where the pollution goes. The smoke from Siberia goes around the world within a few weeks. Okay. So you have forest fires here, but then the effect could be felt in Canada. It's affecting the agriculture in Canada. This is a lake feeding one of the major cities in India. This was in May 2018, and within 1 year, it is completely dry. Okay. So if we were regularly monitoring, we would be aware that the situation is going to happen. But unfortunately, we were not. So agriculture is becoming data rich, but data is not the same as information. Information is not the same as knowledge, right? We just have numbers. We're gathering numbers. So the emphasis now is on becoming data smart from data rich, right? So how do we do that? The same table, if you see above this, in the agriculture knowledge generation part, there are no layers, especially in the farm production and inputs area. And that is one of the places that Skoltech is trying to make an impact. Right? So one of the major users of all this data is what we call digital agriculture, right? What is digital agriculture? It is simply the tools that help us to digitally collect, analyze, and share the data. It's also called smart or e-agriculture. And you guys might have heard of precision agriculture, which is a sub part of digital agriculture, right? So you have the crop life cycle, right? You put the seeds in the ground, it germinates, it starts growing, matures, starts flowering, and then you have the crop which you harvest, right? So how can we manage this crop life cycle? There are pre-sowing activities, so which include things like how are the field conditions? What is the health of my soil? Are the necessary nutrients available? How are the meteorological predictions for the season? How much water is available, or some of the other socioeconomic things like what are the market trends? Is everybody growing wheat? So the market price of wheat comes down, or only some of them are growing wheat, some are growing sunflower, right? And also, what do we need to do to prepare the soil for the coming season? During the growth phase, we can provide advisories on when to irrigate, when to apply fertilizers, what kind of adverse weather is expected in the near future, and also diseases or pests that may harm the crops. You can also say when to harvest, depending on the weather conditions, on the logistics, market dynamics, storage availability, things like that. Right. So digital agriculture is probably easiest to apply in greenhouses because the entire environment is controlled, right? You don't depend on nature most of the time. So we see a lot of smart greenhouses now, where you have sensors for a number of different parameters like temperature, humidity, the amount of light, the leaf wetness, how much salt is in the soil or in the water, all these things. You have analytics, including machine learning, artificial intelligence, which sends back instructions for the equipment to be controlled within the greenhouse. So just one example by Bosch in Japan. There was a study done where they monitored about 100 factors. They were able to predict disease infection with an accuracy of greater than 90%, reduce pesticide use by 30%, and increase yield by 15%. So this is by digital analysis, right? Digital agriculture. So we can create a network of sensors. Like I showed earlier, the critical zone observatories usually have a network of sensors. So you have sensors in different resolutions, different platforms. Could be satellites, could be drones, could be on-ground sensors. Send them all for storage and analysis. Make the modeling, could be physical modeling, mathematical, could be statistical. Take that information and provide instructions for better operational management, right? But then, if you're doing on-ground sensors for agriculture, you cannot have sensors all over the field, right? You have a large field, but you cannot have sensors everywhere. It's going to interfere with the operations. They're going to get damaged. So how can we reduce this to just maybe 5 or 3? Right? So we have done some studies where we've shown that instead of using, for example, 87 places to measure, we can get away with just 5. And the accuracy is more than 95%. If the heterogeneity in the soils, topography, vegetation is a little more, maybe we need a few more sensors. Or maybe sometimes, if it is so heterogeneous, we cannot reduce the number of sensors. In that case, we'll have to think of maybe remote sensing and not on-ground sensors. Okay. Does anybody recognize any of these people? Look carefully. No? Good. Because they don't exist. They're all artificially generated photographs by artificial intelligence or machine learning, right? So it's what we call the adversarial generative networks, generative adversarial networks. And we thought if we can produce photographs of people, can we do the same thing for soil conditions, for fields? Can we create a digital twin of my field, of the soil conditions of my field, right? So we tried the same thing. We took soil samples, scanned them using X-ray tomography. So these are the scans. and we trained a generative adversarial network to see if we can get similar soil conditions. So why is this important? We cannot go and measure the soil, the field everywhere to see where the cracks are, how they are connected, what is the porosity, what is the pore connectivity, things like that, right? We cannot dig up the whole place. And once you dig it up, it's already changed the structure. But if we can do just at a few representative places and then create a digital interpolation, we are in much better shape. So our digitally created fields match the real fields pretty well in our experiments in terms of porosity, pore size, and pore connectivity. Right? So we've done that on a 2D scale, and we are now working on a 3D version of the same. And this was actually funded by Microsoft's AI for Earth initiative for us. The other one other thing that we're looking at is classification of crops. Take an image from the satellite like this and turn it into this, where each color is a different crop, right? We need to know what crops are being grown in each field. So how do we know that? We know that different crops at different stages of their growth reflect the incoming wavelengths at different rates. Okay, so this is where the spectral resolution of the sensors are important. So higher the spectral resolution, the better the differentiation between crops or stages of growth of the crop. So this is another example where we have done this for certain crops, and we were able to get a pretty good accuracy of prediction. We have tried that with different methods, of course, and this was funded by the Russian Agriculture Ministry. Sometimes satellites have problems, sensors on satellites. Right? Could be an instrument failure. Landsat, a major provider of, if you look at Google Maps, most of the imagery that you see as satellite images are provided by Landsat. Okay. So there was an instrument failure which created these bands. Right? So, or they could be clouds. There could be a plane flying somewhere here, which is covering the ground. So you can't see what is happening beneath here, right? So how do we repair this? Traditionally, what used to happen is you take a time series, you have one image which is corrupt, you take the image before and the image after, do an interpolation, say you're close enough, right? Not a bad idea. But then if you look at places like Moscow, where the number of clear days in a month, the highest is 11. And Landsat has a temporal resolution or a revisit time of 16 days. So it comes back to Moscow every 16 days. The chances of me getting a clear picture of Moscow, the probability is almost zero, right? So I can't really use this time series method. We need to look at something else. So we came across this method developed at Skoltech for restoring old pictures, photographs. And it is called deep image prior. So if you have old damaged pictures which you have scanned, how can you fill them in? Right? So these guys said that all the information necessary is contained within the image. You don't really need an image from before and an image from after. We applied the same thing for the satellite images which were corrupted. So this is the original image, and then we progressively corrupted the image with missing information up to 55%. Right? And even at 55%, the darker the green, the closer the match, the accurate the reconstruction. Right? So we still get an accuracy which is on par with the multi-image methods. So we do all this. What is the next step? Where are we going with this? As I said before, we would like to create a digital twin of our farms, right? We monitor all the conditions, the soil, the plant, the chemicals. So physics, biology, chemistry, all of them are monitored. Sent back somewhere, you do some calculations. Send back instructions to maybe the harvester, maybe the machine that sprays the fertilizers. How much, where, when, right? So to do that, lately we have been concentrating on something called envirotyping. So are you guys aware of genotyping and phenotyping? Right? If you're not, genotyping is basically classifying based on your genes or genetics. Phenotyping is classifying based on how you respond to certain conditions. And envirotyping is an extension of that. We are classifying based on the environments. Okay? So suppose I have this piece of land, we have some trees, we have some animal farms, we have grass, other farms, whatever, right? So how do I take this, convert it into a grid block? Each one of these blocks has its own value for different environmental parameters, right? It could be the moisture in the soil, how wet the soil is. It could be how much rainfall occurs there. It could be the temperature, right? So these are all dynamic. They change very fast with time. So it could also be more static things like what is the soil type? Is it more sandy, more clay, loam? It could be the topography, which probably will not change naturally for thousands of years. Or land use, is it being used for growing crops? Is it a forest? Is it a grassland? Is it an urban area? Or it could be any of 100 different things in between, a very dynamic or a very static variable. So the complete set of all these variables is called an environment. And a particular combination of all these factors is what we call an envirotype. Right? So each one of these grid blocks is unique. They may have the same temperature and rainfall and soil moisture, but the land use might be different. Right? So why do we do this? It helps us understand better how the genetics of the crop and the environment interact with each other. You know, there is this big debate. It's not just for crops, but also for us humans and animals. How much of what we do or what we are is nature, that is genetics, and how much of it is nurture, which is our environment that we grow in, right? So this helps divide that ratio to get that better. So how will that help improve agriculture? Basically, we can choose site-specific varieties of crops. The wheat that is grown in Krasnodar might not be the same variety that is best suited for growth in Belgorod because the environment there is different. So you need a slightly different genetic makeup of the crop. And it might not be the same that is grown in India. Right? Also, if you have a variety that you already have in your hand, where is the best place to grow it? Right? So both ways this works. And also, you can say, okay, this environment does not have a high potential for certain diseases because it's too cold or it's too hot for certain diseases to occur. So you can engineer your crop to, you don't need to be worried about that. So the resistance can go out of the window. Envirotyping as a field is pretty new. It is since the 2015, 2016, around that. But a lot of the components that we use for envirotyping, we have been doing for a couple of decades now. But it's only now that we are sort of bringing them all together. And the primary tools for envirotyping are mainly remote sensing as the data source, geostatistics for verifying the data, cleaning up the data, things like that, GIS for visualization and mapping, and then the process or data-based models for the analysis and prediction. So how will it help? We did the study here. Okay, let's say I have a farm somewhere in India here, and I want to grow something. What do you want to grow? Anything? Sorry? Cotton? Cotton? Okay, yeah. So I have two other sites where cotton is grown, different varieties. Okay? And I want to know which one is the better variety to grow here. There are two varieties, let's say north and south. They both grow very well in their locations. So which one would you choose for your new site? Just biologically. By logical thinking, you would say the one that is closer is probably better suited, right? These are in this same region. This is much further away. So if the variety is growing well here, it will probably grow well here too. That's what I would do too. But then we did an envirotyping study. And we found that this location is a completely different envirotype compared to these two. So geographically, they may be same. Geostatistics, if you use straight away, you would still be using this. But envirotyping tells you that's wrong, and we should be using the other one. Right? So just by this, we know that it's better to use this, you'll get more yield, better profits. It of course depends on the timelines that you use. If you're looking at annual, you can see the differences between 2016 and 2017, right? Similarly, the other years. If you're looking at a window of just 30 days, you have a completely different picture compared to 365 days. So we also need to look at what is my growth period? What is my growth season? Are we looking at winter or summer, spring? Right? So a lot of different factors come into the picture here. Let me just skip the slide. It's about certain packages that we now have in R, which can do this sort of comparison of different locations and say how similar they are to each other. Right? So in the study, we found that the authors found that Brisbane and a location here were very similar. Although we would say, just looking at the environment, they might be very different. Right? It's not just different locations, but also in what parameters they are similar. We do a lot of about 20 to 30 different environmental parameters, about 10 different soil parameters, and now we are in the process of including genetic parameters into this kind of analysis, which shows, okay, location 8 and 7 are very similar to each other, because you can see that in all the precipitation dependent parameters, they are very similar. But if you look at the temperature dependent parameters, they're not so matched, right? So if you have a crop that is more sensitive to temperature, you need to be careful when you're taking from here and planting there. But if it is dependent on water availability, then yes, you're welcome to do this, right? So drought is another thing that is a significant concern. Russia, we would generally not associate with drought, but in the last few years, the south of Russia has been experiencing drought every year. And every year, mid-season, the estimates for the wheat yield of that season is downgraded. Right? It's not just for crops, it's also for animal products, because the temperature, the lack of feed, all that affects even things like milk production. Right? And we can see that the drought in the southern region is increasing every year. So how do we incorporate this into our predictions for future yield? So a G20 climate risk analysis for Russia, agricultural drought. Okay, let's just think of this in simple terms as best case scenario, worst case scenario, most likely scenario. Okay, for the next 25 years. So if you look at it, agricultural drought is going to increase most likely by 16%. The frequency of drought, how often you get drought, is also going to increase significantly, right? There's going to be more heat waves frequently and more runoff because you're going to get more melt from the northern regions. The permafrost is melting. There are more regions in the north which are no longer experiencing as severe winters as earlier or as frozen as before, right? So all this comes into the picture. So we did the study in Krasnodar where we used crop health in terms of a parameter called normalized difference vegetation index. More green, the better the crop. If it is diseased or if it is dry, the leaves automatically become red. So it is less healthy, right? We also can extract how much water is in the crop, which is a better indication than NDVI because NDVI is showing what has already happened, but the water availability shows you what can happen in the near future. We put them together to create what is called a normalized difference drought index for the region. Right? So these are all farms of a particular agro company in Krasnodar. So you can see a lot of places there's going to be a lot of drought. Right? And we use this information to and forecast it using machine learning methods and use the history of relationship between the drought or the environmental conditions and yield to be able to predict their yield for sugar beet crops depending on when they are harvesting every year. Now, of course, we can then put that into a range, and we found that with just 9 years of data, we were able to make predictions for up to 3 years in advance. The dark lines here are the traditional methods that are currently in use, which have an accuracy of about 50% in terms of yield prediction. So at the beginning of the season, they make this prediction that, okay, I will get 100 tons from this field, but the accuracy is about 50%, right? We were able to increase that to about 75, 78% by just incorporating the drought into the analysis. So we are now in the process of expanding this into by using more. Sorry, this got messed up. By incorporating more parameters into the analysis, we are calling it easy, although it's not really easy to do this, but just an easy way to catch people's attention, called environment augmented smart yield. Right? So we do smart yield recommendations for fertilizer and water applications, and also early warning for diseases and pests. So it reduces the operating costs and damage, and also increases the productivity. So, in summary, I think we can agree that agriculture is now a high-tech industry which uses a lot of digital tools. It is data-rich now, and we need to become data smart. And that envirotyping is one of the major ways that we can proceed forward in this. Thank you very much for your attention. And if you have any questions, I would be happy to answer, or you can contact me